So you recall that in the last unit, we took a look at how do we solve for unknown side lengths and unknown angles and solve triangles when they were right angle triangles. Again, a right angle triangle is any triangle where one of the angles is 90 degrees. Okay, um, but how can you determine the dimensions of any triangle? So there are triangles out there in the real world and whatnot that are not 90-degree triangles. And so how do you figure out the side lengths of one of those, or an unknown angle in one of those if you need to, particularly if you're using it in some form of design? So this type of thing comes up in surveying and in construction and in architecture and engineering and so on and so forth on a fairly regular basis. So let's take a look at this particular investigation. So let's say that an architect designs a new building and it's supposed to be 12 meters wide. Okay, so the roof consists of rafters on two different lengths, or the two rafters. And again, a rafter is one of these things. Okay, so the angled pieces that help to support the roof. So the rafters are two different lengths and they meet at the top with an angle of 80 degrees. Okay, so the long rafters make a 135-degree angle with the outside exterior wall. Okay, so how long should the carpenter cut the short rafters? So we want to figure out the length of both the short rafter and the long rafter. So in this instance, we've got a couple of things that we need to investigate. We know we have this particular diagram. So question number one says, at what angle does the long rafter make with the horizontal? So we know what this entire angle is from the vertical to the top. We know what that entire angle is, and this entire angle is 135 degrees. I want to know what is the angle from the roof to that horizontal piece. So that's what we got to figure out. Okay? So in order to be able to do that, we need to recognize that this is a rectangle rather on the bottom. And the angles of a rectangle on the bottom, okay, this angle right here, that's 90 degrees. Okay, so if I want to figure out what my angle is going to be, then I got to take 135 degrees and I have to subtract 90 degrees from it. Okay, and when I do that, I end up getting 45 degrees. So my rafter, or my long rafter rather, from the horizontal to the rafter makes an angle of 45 degrees. So what then is the angle of the short rafter? Okay, so I want to know what this angle is in blue. Okay, well, since I now know that this angle right here, that's a 45-degree angle, and I know that at the top I've got an 80-degree angle, I want to figure out this short rafter. Well, I can take 180, because again, all three triangle, or in a triangle, all three inside angles equal 180. So 180 minus 80 minus 45 is going to equal 55 degrees. Okay, so this angle here is actually 55 degrees. Okay, now for question 3, it says, why can you not use a primary trigonometric ratio to solve this problem? Okay, again, a primary trig ratio is using SOH, CA, TOA. Okay, either using the sine, the cosine, or the tangent ratios that we talked about in the last unit. Well, why can we not use any of these actually? And the reason we can't use any of these is that there are no right angles. Okay, there are no right angles. Okay, and again, a right angle, there are no angles that equal 90 degrees. So because none of the angles equal 90 degrees, we can't use the side law. We can't use the sine ratio. We can't use the cosine ratio, and we can't use the tangent ratio. So based on what we learned last unit, there's nothing in the last unit that we learned that would allow us to solve for this particular triangle at the top. So that means that we have to investigate a different way of using trigonometry to solve this particular problem. So we're going to go through and we're going to determine the sine law. So we're going to try and figure out, well, what does this actually mean? How can we determine what the sine law is going to be if we go all the way across and solve for it? So in this instance, our sine law is going to involve us taking a look at this triangle that we have here on the left-hand side. So we're going to actually measure all the side lengths and the angles of this acute triangle. Okay, acute just means that all of the angles are less than 90 degrees. So in this particular instance, if we go through and we measure, we can actually determine what all of the angles are going to be. Okay. So first off, if I want to measure angle A, well, angle A is equal to approximately 79 degrees. Okay. And if I go through and I want to figure out angle B is approximately 36 degrees if I use my protractor. And then if I go through and I carry on, I know that angle C is 65 degrees. Okay. If I then measure the length of all of the sides, okay, so the side across from A, okay, so here's angle A, so the side across from A is little a, and little a is approximately 7.5 centimeters. Okay. The side across from B, so here's angle B, so across from B, that is going to be approximately 4.5 centimeters. Okay. And the side that is across, the side length that is across from angle C, that is going to be approximately 7 centimeters. Okay. So if I go through and I've measured this and I have my angles, let's look at the ratio between both the angle and the sine of that particular angle. So I've got my angles all up there. So if I'm looking at side A, then what I end up with is 7.5 divided by the sine of 79 degrees. If I look at side B and angle B, I have 4.5 divided by the sine of 36 degrees. And if I look at the relationship between angle C and side C, I know that I've got 7 divided by the sine of 65 degrees. Okay. Well, if I actually compute this, if I want to figure out what that actually equals, what's interesting to note is that if I take 7.5 and I divide it by the sine of 79 degrees, that actually equals about 7.64. Okay. If I take 4.5 and divide it by sine 36, that's actually going to equal about 7.65. And if I take the sine, if I take 7 divided by sine 65, that's going to equal approximately 7.72. So we need to take into account the fact that some of the lengths weren't perhaps measured 100%, or maybe one of the angles was off by 1 degree or something like that. But I think it's pretty clear that we notice that all three ratios for side A, side B, angle B, side C, sine C, that all three ratios are very, very similar. They're almost the same. Okay? So all the values are almost the same. So they're almost equal to each other. Okay, and because they're almost equal to each other, there is actually a connection. Again, you have to bear in mind that there is obviously some kind of error in terms of our exact measurements and so forth. But because they're almost equal in a perfect world, they actually are 100% equal. Okay, and so we can determine what the sine law is from this particular piece. So in this case, the sine law is actually the length of side A divided by the sine of angle A is equal to the length of side B divided by the sine of angle B, which is equal to the length of side C divided by the sine of angle C. Okay, and again, you'll notice that on the top we have A, B, and C all in lowercase letters because they indicate side lengths. And in the bottom, we have sine A, sine B, sine C. A, B, and C are all capital letters on the bottom because they represent angles. Okay, and so what this means is that the two sides, or so long as you have a side angle pairing, you can use the sine law in order to figure out both unknown side lengths and unknown angles.